Hello, this is Mr. Ratoon, and this will be a review for Learning Set number 2, Why Do Some Things Stop? This is the PS2 book, and this is a review for our second test. So what we're going to do is we're going to take a look at some potential questions that could be on the test. For example, this first one that we see right here. Let me put this up so we can only see part of it. So which of the following types of energy is potential energy? Circle all that apply. Well, if we were to take a look at this one right now, and I'm going to grab a pen. Let's go with purple. So we look at A, gravitational energy. So think about what we studied in class. So a type of potential energy. Is gravitational a type of potential energy? If we remember, it indeed was a type of potential energy. Now, kinetic energy you should be able to cross off right away. And it's not even a choice because potential energy and kinetic energy are the opposite of each other. So then thermal energy and sound energy. If we remember, thermal energy is connected once again to kinetic energy, and sound energy is also connected to kinetic energy. Thermal energy is those nanoscopic particles moving in a random motion. And sound energy, there is no randomness. There is no randomness. There is a pattern there. So these both would be crossed off. So there's actually only one here for gravitational energy. Now, if we look at the next question, a cold can of soda is taken out of the refrigerator. It slowly warms up until it is at room temperature. Once the soda has warmed up, it has more thermal energy than it had in the refrigerator. Where did this additional energy come from? So when we look at this, the thermal energy was already in the soda. If the thermal energy was already in the soda, it would already be the temperature it's at, or the warmer temperature. So that's not a good answer. The thermal energy came from the air surrounding the soda can. That one sounds pretty good, but I'm also going to read all the other ones because that's a good thing to do with the test. Read all of your, all the samples, all the choices just to make sure. So it says the thermal energy came from the air surrounding the soda can and from the soda itself. Well, we already said it can't come from the soda because if the thermal energy was already in there, wouldn't the soda already be warm? And the thermal energy came from the refrigerator. Wait a minute. We took it out of the refrigerator. So this can't be it. So we only have one choice, and it is B. So by going through and reading them all, sometimes it's easier to eliminate problems or choices. That way it's easier to pick the final one. So let's look at these two problems. Let me pull up a shade here. And so what determines the amount of thermal energy of an object? Circle all that apply. So I'm going to grab another pen. Let's grab green this time. So temperature. Does temperature have to do anything with thermal energy? Yes, it does. If we remember, it has a lot to do with thermal energy. We talked about hot tea versus cold tea. How about speed? I'm not really sure about speed. Let's go through some of the other ones. Mass. If we remember the lab, we talked about having a large beaker of water and a small beaker of water. And if you remember, the larger one had more thermal energy. So mass must have something to do with it. How about springiness? Nah, that has more or less to do with the elastic energy. How about speed? Well, we're going to cross that one off because as the temperature and the mass increases, we have more thermal energy because the nanoscopic particles are moving faster and faster. And that has to do with the temperature. As the temperature increases, the particles are going to move faster. If we take a look at the next question that we're going to use as a review, which object has more thermal energy? So we've already talked about thermal energy once. Let's see if we can make that stick. Which object has more thermal energy? A large pot of water or a small pot of water? What's the temp? Ooh, it's the same temperature. So we're only dealing with mass here. So what do you think? If it's a large pot of water versus a small, the larger one should because it has more mass. So let's see, both pots have the same. No. The small pot has more thermal energy. Wait. If it has more mass, it has more thermal energy. That shouldn't work. The large pot has more thermal energy. I think it's this one, but I'm just going to read the last one. There is not enough information. Nope, it's definitely this one because there's more than enough information. So it says it's the same temperature, so we know what the temperature is, and it's a large versus a small pot, so we know what the mass is. So we take a look at another potential question. One thing I'm going to have you do on the test is you're going to have to create an energy conversion diagram for a bouncing ball. A diagram has been provided for you, and the diagram, I don't have it right here, but it's going to show a ball, and that ball is going to be dropping. It's actually going to look like this, and then it's going to be hitting the ground. Here it's going to be deformed. Here it's as if it's just leaving. Here it's going to be again. So it's going to be 1, 2, 3, 4, and 5. And you're going to have to draw me a key for GE, which is gravitational energy, KE, which is kinetic energy, elastic energy, and thermal energy. Now, there's a couple of variations I'm going to accept. Obviously, number 1 over here should have some GE because it's got some height, should have some KE because it's dropping. Now, let's talk about thermal energy. Some people argue that it's going to have a nanoscopic particle of thermal energy. It's going to have just a little bit because there is that friction between the ball and the air. So if you have a little bit of thermal energy there, I'm okay with that. Now this may look like it has quite a bit, but remember, what these energy conversion diagrams really show is just what types of energy there is, not necessarily the exact amounts. So for the second one right here, you can see that it's touched the ground, so it no longer has GE. Okay, it's still moving, so it's going to have some KE. Now, we got to ask ourselves a second, is there any deformation? Well, if you look, it just touched the ground. There's no deformation yet, but we still have that leftover thermal energy. So if you have a little thermal energy here, I'm okay with that. Now, if you look at this one right here, which is 3, this is where it's mainly deformed. Now, at that exact moment where it's completely squished or deformed, it won't have any KE there. So it should have, you see the checker right here, it should be E because it's got elastic, and I'm going to call it, I'm just going to write it shorter because I can't write the whole thing in there. But remember, EE could be electrical energy or elastic energy, so that's why I wrote elastic right up here so we wouldn't get confused. And now it's going to start getting more thermal energy, not only from the ball moving through the air and coming in with friction of the air, but also on the bounce as well. So again, once it leaves, you got 4 over here. It still doesn't have any gravitational energy because it hasn't picked up. It's going to have a little bit more KE again, and it still has some of that leftover thermal energy. Now, it's not deformed anymore, but that thermal energy just can't disappear. And then all of a sudden, 5, you see, we start to have GE again because it has some height and still some of that thermal energy. Now, if I'd wanted to, maybe I could have marked the thermal energy up here and say, okay, it's already lost a little bit of thermal energy. That would be acceptable as well. So on a test, make sure you're able to draw an energy conversion diagram and be able to use GE, KE, elastic, and thermal energies. Now on the test, another thing I'm going to have you do is I'm going to have you take a look at a diagram similar to this. Now this could be a pendulum, could be a ball bouncing, but we've got the height, we got the number of swings for the pendulum. And if it was the ball, it would be the number of bounces. So each time you can see that there's less and less height. So the graph at the right illustrates the maximum height the pendulum reaches after consecutive swings. Explain why the maximum height gets smaller with consecutive swings. So what I'm really looking for is an answer similar to this one right here. It says with each swing of the pendulum, the bob, and remember that's the bottom of the pendulum, the bob transfers energy to the surrounding air, leaving it with less energy than before, so it can only reach a lower height with each consecutive swing. So make sure you talk about how it is losing energy. A lot of students will just talk about it losing energy, but make sure you talk about it losing energy to the surrounding air. If you just say it's losing energy, I'm going to give you some of the credit, but I'm going to think, where does that energy go? Energy cannot just be created nor destroyed. So if it's losing it, where is it going? So this is where if you explain that it's losing energy to the surrounding air, that's where you're going to get maximum points. So this is one of those questions I'm going to start right here that I'm really checking for your deep understanding of this topic. And this might be one of the differences between you getting a 3 and you getting a 4. Now, looking at the same diagram here, does the diagram above contradict? That means, does it go against the idea of energy conservation? Remember, energy conservation, we go back to the idea that energy cannot be created nor can it be destroyed. So does this diagram contradict the idea of energy conservation? And when you first look at it, it looks like it would. It looks like the energy is just disappearing. But what's happening to that energy? So explain your answer. Does the diagram contradict the idea of energy conservation? And you'll also notice that it include energy systems in your answer. So my answer is no, it doesn't. Well, the energy of the ball decreases, and we can see that it's decreasing up here. It's going down. The total amount of energy of the ball and the surrounding remains constant. This means that the energy remains constant within the system. So the energy, even though it's getting less and less, it's just transferring to the system. So this might be the pendulum as it swings back and forth. It's going to have some friction. It's going to lose some of that heat, that thermal energy created from the friction is going to be lost to the environment. If it was a bouncing ball, it might be sound and thermal energy that's being lost to the surrounding system. So we can't look at it and just simply say that, ooh, it does contradict. No, it doesn't. It just means the energy is going someplace else. So here's one of those things, and this may look similar to the CER that you will take or you may have already taken. It says, analyze the bouncing ball illustration below. Circle and explain which energy conservation diagram illustrates what is happening at point 2. Okay, so I have point 2 right here. And I've got two choices. I've got this one right here, where the GE is increasing and the KE is decreasing. And I have the one down here where the GE is decreasing and the KE is increasing. So what I have to do is I have to be able to pick which ones. Now both graphs looks exactly the same, but the GE is increasing in one and it's decreasing in the other. So I've got to be able to figure out which one it would be. Well, a couple things. You see how the height is up here? Now all of a sudden the height is lower. What that's telling me is that it's dropping. And if it's dropping, that means it has a lower height. So now all of a sudden start to look at this and say, okay, at a lower height, I'm going to have less GE. Also, as this ball is bouncing, it's going to be picking up speed, which means the KE should be increasing. So when it says circle the one that I think is it, I'm going to circle this one. Now, for your explanation, I chose the second diagram. The GE is decreasing as the ball drops because its height is decreasing. I chose KE because as the ball is picking up speed as it falls, its KE is going to increase. Now, a lot of students will just simply answer this when I ask for an explanation. They'll just simply say, oh, because the GE is decreasing or the KE is increasing. Well, let me ask you this. How does that explain why this is it? You didn't really explain. So in here, I'm going to be looking, did you talk about how the height is decreasing? Did you talk about how it's picking up speed and that's why the KE is increasing? So I'm going to be looking for both of those in your answer if you want full credit. So I'm going to start this one again because this is another one that I'm really looking for some deep understanding. And again, how you score on this, you might get partial credit, but you may not get the full credit because you don't explain about the height and picking up speed as it's dropping. And that's another one of the questions that really differentiates between 4s and 3s. And one last question I'd like to go over with you here is you have a 400 milliliter mug with hot tea and a 400 milliliter mug with iced tea. So we have hot tea, we have iced tea. You notice the mass is the same. They're both 400 milliliters, so that's not going to change. And some of you might be saying, well, isn't milliliters volume? Yeah, but if it's the same volume, it's going to have the same mass. So which mug has more thermal energy? And again, I'm going to star this one right away because I'm going to let you know this is the third question that really is going to differentiate the level 4s from level 3 students in my class. So here is a typical 1-point question. Which one has more thermal energy? The larger mug of hot tea has more thermal energy because the water is hotter. This would give you 1 point. But if you want to earn both points, the larger mug of tea has more thermal energy because its molecules are moving faster. Thus, it has more kinetic energy at the molecular level, and as a result, it has more thermal energy. So this is a much more detailed answer. It tells me that you understand that because it's warmer, its nanoscopic particles, those molecules of water, are moving faster. Doesn't necessarily mean there's more of it because the volume is the same. The mass is the same. It just means that those molecules are moving faster. So, this was our review. As always, if you have any questions or concerns, please check with your science teacher, Mr. Phillips, or myself. Thank you.